Hello and welcome to our November Wednesday with Wing. This month we have Tristan Roberts speaking about low enthalpy geothermal in Scotland. Just before we start, a little bit of housekeeping. Everyone's going to remain muted and the webcam's off automatically throughout. But if you want to ask some questions, please do, because we'll have a question and answer session afterwards. You can use the Q&A function on the side. So welcome, Tristan. Thank you so much for coming along today and talking. Tristan is a second-year PhD student within the Geo Net Zero Centre for Doctoral Training at the University of Aberdeen. He is investigating ground source heat pump technologies in superficial aquifers in Scotland and the potential that they have to provide decarbonised heating and cooling to a variety of settings, including industrial processes and isolated rural communities. He is using GIS software to audit the existing data and a combination of mapping, geophysical and modelling techniques to accurately assess the suitability of glaciogenic superficial deposits. So without further ado, Tristan, if you'd like to share your presentation and get started.
I will indeed. Okay. So you'll have to tell me if you guys can see what are you guys seeing right now?
So we're seeing your slide set up.
Okay. Sorry, I've never used this one before, so.
Perfect.
Okay, so
yeah, we can.
And that is good. Okay. One moment. Yes, I was just checking that I've got it all. Okay, so yeah, thanks for having me. I'm Tristan, as you've introduced. So I'm at Aberdeen Uni. I'm in my into my third year now of being there, so it's about halfway through for me. I've done 2 years, got another 2 years to go. My entire project is about the low enthalpy geothermal potential of shallow aquifers in northern Scotland. What I'll be talking about today is pretty much the work I've done on that so far. So that includes most of Scotland, well, basically all of Scotland. I've made a geothermal potential map, which is what you're seeing on the right, just here. Yeah, a sneaky preview. And I'll go through all this and tell you what I've made. So Hez has told you about GeoNet Zero, so my supervisors with the British Geological Survey, and Tamrock also gives a little bit of advice here and there on the project, which I'm very thankful for. So yeah, I'll go over a bit of context and introduction, and I'll tell you how I've built my resource and what it's talking about, and then the findings and results. So in terms of low enthalpy geothermal, I'm looking at mainly shallow deposits, so I'm looking at superficials. I'm looking at ground source heat pumps and district heat networks and how we can access the very low temperature geothermal resource, which is relatively easy to get at. So the image I've got on the right is a picture of Brooks Park in Inverness. And I've got it here, one, because I'm hoping to go out and do some field work there in the next year, in the coming year. But also because it kind of just shows a nice example of the sort of situation where I think this type of geothermal can have one of its greatest impacts. So you've got sort of on the bank here, you've got sort of domestic housing and some neighbourhoods, and then on the other side you've got some leisure centres. This is the leisure centre here. You've got botanic gardens, and this is an ice sports centre, and you've got lots of open green space alongside these kind of high heat demand areas. So that's the kind of region or urban setting that I'm most interested in. So my general aims are to sort of promote the utilisation of ground source heat pumps as a method of decarbonising heating in Scotland, and doing that by auditing the geothermal potential from shallow groundwater and showing people, businesses, town councils what is actually what resource is actually there. I want to do that by creating a dynamic tool that visualizes the sort of input and external data to allow non-experts to understand the geothermal potential within the context of their communities. So I'm talking about town planners and councillors and community-led projects is the kind of thing I'm aiming this for. But having said that, it doesn't have to be. It's not limited to those kind of people. And yeah, and to create a resource which is accessible to everyone, basically. So with that in mind, I think it's useful to bring up sort of the fair data principles or fair data management principles, and that's that as we create data resources, it should be findable to both people and machines, so that you can run a search and you can find data which you can use for any other type of research that you may be doing. Make sure that it's accessible, so that once you've found it, you can actually open it and use it and understand it, to make sure it's interoperable with different data sets, and so you can modify it and understand it and analyze it, and to make it reusable. So I think it's a good thing to mention, because I want my resources to fit into these kind of principles, but also because the resource that I've made relies on these principles, and that I've produced new data from publicly available data sets. So make sure that everything's findable and usable to everyone is a very important thing for continuing knowledge. So why is geothermal something we should be looking at? I'm aware that I'm talking to a geothermal group, so I don't have to go into too much detail. But behind my project in particular, we're looking at the sort of climate change and emissions reductions targets acts, which are put in place by the Scottish government. So in Scotland, that's net zero by 2045. In the rest of the UK, that's by 2050, and various other nations have their own versions of that. And the reason why I put this in is that there's a sort of legal push or a legal impetus to try and decarbonise the whole of the UK, really, not just Scotland. So that's the kind of push for it. Heat Networks Act is also important, because that provides a pathway by which we can sort of action a couple of these decarbonising technologies. So heat networks are a really efficient way of heating multiple buildings or districts. And so by using it in conjunction with a ground source heat pump, which is what I'm suggesting, it can be a really useful way to make some large scale impacts. So yeah, so the figure on the right here is looking at the UK emissions in 2019, and it's quite useful, and it just shows that 23% of all the carbon emissions from the UK in that year were just down to heating. 17% in our homes, and a couple of other designations there. But what I'm trying to show here is that heating is a very large chunk of that decarbonisation process. So it demands a lot of attention, and it doesn't always get that kind of attention in the media of renewables, when it's often talking about wind or talking about electricity, whereas heating is a very important issue to overcome as well. I can see why that is so high. On the diagram here, it's saying that about more than 3/4 of the heating in domestic homes in Scotland is done by mains gas. So when we're talking about decarbonising heating, what we're effectively talking about is trying to replace the existing gas infrastructure and networks and pathways which we currently rely on, or at least providing an alternative. So I also like to include this this figure in at this point in the talk. It's looking at the fuel share for residential and commercial heating demand in a sort of range of European nations. And what I like to look at is you've also got the UK and the Netherlands down here, and you've got Norway up at the top around here, and Denmark also kind of around here. And these nations sort of share a North Sea oil and gas legacy. They've all had access to that resource. And it just demonstrates the different approaches that these nations have had to using that resource. You can see the UK and the Netherlands here invested heavily in gas infrastructure, whereas that's quite a different story up in Norway. And you see that a large portion of their heating is coming from district heating over here, and also electricity. And electricity will include heat pumps. I like to include it just because it demonstrates that using district heating and ground source heat pumps and also other types of heating is a viable way of heating a nation by going through a sort of decentralized route rather than a centralized gas mains approach. And just demonstrates that it actually can work. It's not entirely just pie in the sky kind of thing. So in terms of how it works and what type of geothermal I'm particularly looking at, it is for use with ground source heat pumps. So they'll be taking their low temperature heat resource out from the environment. So that can either be through a closed borehole loop or an open loop system directly through to the aquifer, bring water through the heat exchanger into a working fluid, which will then be compressed. That's where your electrical input goes. It warms up the temperature of that working fluid, which then goes through another heat exchanger, and you can then distribute that throughout your home for whatever end uses you have. And it goes back around to an expansion valve, and the whole process repeats itself. And the main thing to get from this is that the amount of electrical energy you need to put in to boost the temperature from the environment you're bringing in is less than what you get out. So the ratio can be for up to about 1 to 5 for the most efficient ground source heat pumps, but you're effectively getting more thermal energy out than electrical energy you put in, and that's quite a useful thing. So if you then put your ground source heat pump into your home, you can use it for radiators or hot water and floor heating or whatever. But this is on a relatively small scale. So this is just for one house. But what shows a lot of potential is by upscaling this to use it in a district heat network. And this is a sort of schematic image of what that could be. So you've got your geothermal resource down here, and you bring it up to a heat exchanger, which distributes that sort of cool but still usable water throughout districts. And then in each one of these larger homes or flats or commercial buildings or whatever, you have a heat pump which can then boost these temperatures up. And that provides a really efficient way of heating all these buildings from a single larger geothermal resource. And one further thing just about district heat networks, if we go back to the introduction where I talked about the Heat Networks Act, part of what's included in that is a requirement for Scottish councils to look into their existing building stock and analyse the potential that exists there for connection to a district heat network. So if you're going to make new district heat networks, you might as well try and make efficient heat networks which can be coupled with renewable technologies, which is why I'm now going to talk about 5th generation district heating and cooling. The main bit to take from that is that this water that you're circulating around the district is relatively cool, which means that the individual heat pumps can use it for both heating and cooling. So you might have some cooling requirement from data centers or from industry or even from other renewable heat sources. And if you put that reject heat into the district heat network system, that heat can then be transported to these other end users and used to heat the home or heat these commercial buildings. So it makes the entire thing more efficient. The difference in these is mostly a design and engineering thing, but it does make a big difference when you're considering the compatibility of different technologies and if an area actually has a suitable geothermal resource to supply the demand that exists there. So this is an image of the different kinds of geothermal which are sort of applicable to the UK. At the right, you've got the deeper high enthalpy systems into sort of fractured granites. That's your sort of Cornwall end member. What I'm looking at is sort of way down here. I'm looking at the shallow aquifers and superficial sediments. And that is sort of truly in the realm of ground source heat. So in Scotland, if something above sort of 8 degrees would be the lowest I really want to be looking at. But you can do useful things with those kind of low temperatures, and anything above that is a bonus. So if we then go on to what I've actually done with this information and this context, it comes to sort of building the dynamic resource that I'm trying to create. So you got to think about what data is actually needed for a geothermal assessment. So I've identified sort of key criteria that is essential for an area in assessing whether an area is suitable for this type of geothermal. And then I've identified data sets, publicly available and accessible data sets, which I can use to represent those key criteria. And those key criteria can roughly be split into sort of heat resource criteria. So these are effectively hydrogeological factors, such as where are your superficial aquifers, and how deep are they, and how productive are they, and how warm are they, and what's their sort of groundwater chemistry like. And then on the other hand, you have your heat demand, which is effectively energy usage, and that can also be impacted by sort of protected areas. But this sort of heat demand is equally as important because you can't transport heat the same way you transport electricity or petroleum or any of these other things. So you've really got to keep your resource quite close to your demand, if that makes sense. So having identified these key criteria in the data sets to represent them, so how can we observe the spatial distribution of these multiple data sets in different contexts? And the answer to that is through GIS, through Geographic Information System. I've used ArcGIS, which is through Esri, but you can use whatever types there are. There are quite a few. But GIS is really useful because it allows the layering and integration of multiple available data sets that can then be used to create an interactive or dynamic resource that can show something like hydrogeological and social data at different levels and different stages of integration. And this means that you can play around with the resource and you can pull up the integral data to it and you can compare and contrast it. So someone who is a non-expert can gain an understanding of why their geothermal resource is assigned as it is and what kind of natural factors are contributing towards that. So that means that the resource then has a high interoperability. If we go back to the FAIR principles, as external data can be overlaid to assess suitability in varying contexts. So external data could be something like connection to the mains gas grid, or could be fuel type, which is being used, or index of multiple deprivation. You can whatever it is, and whatever an end user might be looking for, you can interope that data with the resource. So that brings me onto this table, which I made, which this is the favorability index, and is really the basis of how I've produced that favorability, geothermal favorability map, which was on the title slide. So we again got the key criteria, and we've got the data sets which represent them. And then I've got a sort of 1 to 5 unfavorable to favorable system, whereby we can categorize the data within these data sets and score them. So for each data set that we've got, so we can look at temperature, we can categorize what's in there. So 1 to 3, you're really not looking at anything useful. Above 7.5, you can start to think about what you could use that for, kind of thing, and everything populated in between. And what this does is it puts all these varying data into a common framework by which we can then compare them on the same level. So what I've then done to create the map resource is used a 1 kilometer grid, and each kilometer squared will get a score depending on their on the initial data set. So then, because there are 10 input data sets, each square kilometer will get 10 individual scores between 1 and 5, and then the average of that is taken as a favorability index score, and that's what's represented on the map, which I'm going to show you soon. So if we then go through the different criteria, first one is sort of the coverage of superficial deposits. This is quite an easy one. It's more of a yes/no. Are superficials there? Yes, then you can go and look further in. If they're not, then there's no point because they're not there. This is interesting as well because it therefore creates the study boundary, because you can't look at geothermal resources in superficial deposits where there are no superficials. So that's what this sort of grayed out areas are on the map. So then we have deposit thickness, and this is represented by 2 data sets. The first is the basic superficial deposit thickness model. It's from BGS, and both of them are from BGS actually. And this effectively just looks at the borehole records across Scotland and maps out the superficial deposit thickness across them. What's interesting to note from here is you see there's a lot of yellow, and you can see this sort of red little stripe through there, which might look familiar. That's the path of the A9, and that demonstrates the sort of observation bias, which is in this data set. They built the road, and therefore they can see what the deposit thickness is there. So it's important to show and recognize that while one of the strengths of the resource that I've made is that you can pull on information from varying sources, it also therefore inherits the biases of each of those data sets. So we have on this other data set we've used to represent thickness is the buried valleys data set, or paleo valleys. So paleo valley is basically an ancient river or ice valley that has been filled with glacial or other unconsolidated sediment. In Scotland, that is all pretty much glaciogenics or fluvially reworked glaciogenic material. And they've been quite useful for this low enthalpy resource because they represent areas of deep accumulations of superficial sediment. And since they also follow the path of modern river systems, there's also usually a very large volume hydrological system which also exists there. As I'll show later, they also tend to overlie where cities are, so they can actually form quite a useful feature to take note of. So another key criteria is the superficial aquifer productivity. Again, 2 data sets I've used to represent these. One is estimating the productivity of these varying lithologies by example boreholes that the BGS has taken, and then it extrapolates that across the whole area. So obviously there are going to be biases in this as well, but it is basically the best data there is for this kind of expanse across Scotland. So that kind of highlights as well that the resource is definitely a national scale or regional scale resource. You can't use it to talk about geothermal potential at a site specific level. This is more for looking at a regional scale assessment. The data set we've got on the right is groundwater flooding, and that's used as a guide for unconfined aquifer presence where you might get groundwater flooding in those particular areas. So when we look at temperature as well, it's another factor which is very important, but it's actually very hard to pin down. So temperature of superficial deposits in Scotland is not recorded, basically. So what the map resource relies on is this sort of relation between the subsurface, the shallow subsurface temperature, and the annual average air temperature. So at depths at 15 to 20 meters, the temperature is approximately constant to the equal, is approximately constant and equal to the mean annual air temperature. Above that, it varies depending on the month. So in June, it might be warmer, and in January, it'd be colder. And below that, it increases according to the geotherm or any advective processes where you're bringing in a thermal budget from groundwater. So with that in mind, I've used a temperature data set, an annual average temperature data set to infer the temperature in the shallow subsurface. Ground chemistry is also important. This is more related towards what infrastructure and materials you'll use in a district heat network or the subsurface infrastructure of your ground source heat pump system. So it's looking mostly at sulfates and it's looking at what impact sulfates will have on concrete structures in the subsurface, and you're looking at iron corrosivity levels in this other data set. So both have an impact on what kind of infrastructure you will be developing in a certain area. And the last one again was looking at the heat demand. This is also from the Scottish Government, which looks at heat demand in different areas, and this is a map of different protected sites across Scotland. So once we've got all those different data sets together, we have the raw data here, and we've taken the next step to sort of recategorize the data in there and to spatially visualize them. We can then combine them together. This is the process which I talked about, where we can average the different scores that each square kilometre will get from these 10 input data sets, and you arrive at a favourability index map. What there also is another or different kind of map you can produce by excluding some of these input data. So by excluding the heat demand and protected sites, you can arrive at a similar resource which is only defined by the subsurface factors. And that means that any high favorability or extreme low favorability areas which pop up in this resource, if they're still present in this second one, then it's a fail-safe to make sure that these aren't just artifacts of population density or heat demand. They're actually there in the subsurface. What it also represents is that the resource is dynamic in that sense. This map, and this is a copy of the one that I put on the title slide, isn't the only product of it. This stage of mapping, of data integration, is variable depending on what data inputs you decide are useful for whatever situation you are in, or whatever the context is of your local area, whether you're a town planner or you're a geoscientist. So what this also allows is external data to be included in the map resource. So I'll talk a little bit more about this on the next slide, but you can bring in something completely separate and overlay it onto the favorability index map, and then you can start to understand what the geothermal favorability means for different social contexts. So what that map was, this external data was the percentage of people living in social housing, and this is just around sort of Ayrshire. And the reason why I chose that one just as an example is because social housing represents a scenario which is slightly easier to implement communal heating schemes in than districts where homes are owned individually or by different entities. So this is just one way that you could go about integrating the data with the map resource. And this is a very spatial example of it, a very visual example of it. But once you get into it, you can then look at specifically what populations or what proportions and demographics you have in one place, and what geothermal favorabilities exist in those areas. So it's allowing a user to come in and analyze the geothermal potential depending on whatever factors are important to them. So if you just break down the map resource itself for a little bit, this is it here on the left, a little bit bigger. What we have here on this favorability index score is the range of values you got from averaging out those 10 different data sets. So that's all that this is, and it's color coded in the same way. These are again recategorized for ease of use into the favorable to unfavorable, and these are broken down in this pie chart by area, and then each area is then broken down by lithology and then the aquifer productivity around the outside. So in total, 49,768 kilometers squared, which is 64% of the total land area, has received a favorability index score. High favorability areas, which are, I'm calling the encouraging to favorable levels, which are these two up here, occupy in total just 12.6% of the land area, so not a lot. However, lower land areas generally exhibit greater favorability, and it's particularly true within the Midland Valley, so around this kind of area. Highlands and islands tend to have less or lesser favorability than lowland areas. And high favorability classes exhibit greater sand and gravel contents, which is conducive to more productive aquifers. So that's these pink portions up here. So encouraging and favorable, you've got more sand and gravels than you have in the unfavorable. And that's useful to know because those are target lithologies. They'll be highly productive. And you can see that's also reflected in the higher well yields you're getting around the sides here. So these dark blues, there's larger proportions up in these categories. But what's interesting as well, or at least noticeable, is that you also get more of these green lithologies occurring with that. And those are clays, silts and sands. And that really reflects the sort of heterolithic nature of glaciogenic quaternary deposits in Scotland. So you don't really get one without the other. So that means that even if an area is suggested to be a high favorability for geothermal, for this type of geothermal, you still need to really seriously look at the site-specific parameters and what the hydrogeological properties are of the space that you're looking at. The other thing to note is that large urban conurbations often overlie high favorability areas. This reflects how they can often co-locate with features that contribute to a high favorability score, such as thick superficial deposits or low altitude and therefore warm temperatures. So that's why you're sort of looking at sort of Glasgow, Edinburgh, Inverness tend to be on quite favorable, quite green splotches on the map. So one of those reasons for the high favorable sediments underlying cities is the buried valley distribution. So if we look here, we can see that cities have preferentially been built on these features. So these different cities here, you can see the thickness of buried valley systems, which you can see here around Glasgow, around Stirling and Inverness. And that's just showing that there's a coincidence between where cities developed and features that are actually quite beneficial to low enthalpy geothermal. So I actually suggest that there is quite a large potential to tap into these resources in the regions where we need the most in these high heat demand areas. And the reason why that is just because buried valleys tend to be, well, they don't tend to be, they are formed where big ice streams and big fluvial systems have descend down to the coast, and that is also areas where you have these large plains. They're quite fertile. They're on major river systems. So there's lots of trade. So there's a coincidence almost, that the buried valleys form a positive area for both cities, but also low temperature geothermal. And this is also an example of using the integral data of the map resource to then go and understand the geothermal potential in a particular area. So we looked at the buried valley data set and we're comparing it to the produced resource. So an example of doing something similar, but this time with external data, we can look at settlement population. So this is around Aberdeenshire, and you've got these different towns, and we can integrate that with the favourability index score. And what I've done in this one is I've actually integrated it with the data properly this time, and you can see that the labels have the town, the favourability score, and their population. So when you kind of extrapolate that or kind of observe that on a national scale, we can see that more than 20% of the Scottish population actually live within an area of the highest favourability index category. So if we're looking at this this cumulative frequency plot here, this is the cumulative frequency of populations within the study boundary and settlement frequency, which is this line here, and they're colour coded by their favourability score. So this is the most favourable up here, this is encouraging here, and so on. So by looking at population distribution alongside the favourability index map, we can see that 20% of the population live within this highest FI category, and approximately 60% live within the encouraging and favourable category, which is these two smaller sections here. And this is despite that these categories, if you remember, form just 0.6 and 12.6% of the total land area, respectively. So this tells us that there is significant potential for heating decarbonisation by just placing a few well-placed or well-designed systems. And it also reflects that while most settlements have a lower favourability score, see the peak is down around here in a neutral area, most people actually live in a small number of large urban conurbations with high favourability. So despite this forming a very small little sliver of land over here, it actually still represents a very strong opportunity for decarbonising using district heating and low temperature geothermal. And it's worth saying as well is that this is a trend which is observed in when we remove the above ground factors as well. So that's just what this chart is showing here. We've got the below ground factors map, and you can see that the favourability index values are still elevated above the background values, despite removing heat demands from the equation. So that's indicating that this is a result of an actual geological feature in those areas and isn't an artifact of population density. So one of the final things I wanted to show was talking about uncertainty. So I suppose what I showed earlier on with the input data sets, and where I showed you the path of the A9 and areas where there was observation bias, it's still important to observe that uncertainty throughout the data set and form a separate map which can visualize that so that people can understand the accuracy of the actual resource. So what I've done here is in a very similar methodology to the favourability index. I've just taken a range of different biases, and I've graded the magnitude of them, and then for each data set input, I've scored them, and I built up a map in the same way, which is this one. So what this is effectively showing is where we actually have the most data. So a lot of the maps which the original map was produced on are extrapolations. So the darker green areas show where there's more genuine observational data than extrapolated data, and that's just an important thing to recognize throughout the resource. So generally, to conclude, so I'll produce a novel geothermal favorability methodology and use it to create a dynamic tool, which is ideally is to aid early stage policymaker and community decision making. So it should be useful for people who aren't geoscientists. So the idea is to try and make geothermal or geoscientific knowledge accessible to the people who actually have to make decisions and planning decisions in various communities. And that isn't just in big towns and cities, it can be on smaller rural places. So the tool allows the visualization of input, produced and external data to allow non-experts, that's basically what I said, to allow non-experts to understand geothermal potential within the context of their own communities. Significant potential to decarbonize heating exists where high favorability areas underlie large urban conurbations, and 60% of the population live in areas where further investigation into ground source heat pumps and superficial aquifers is warranted. And that is pretty much me. Thank you very much for listening, and yeah, I will de-share my screen.
Thank you very much, Tristan. That was a brilliant presentation. It's really interesting to see where you've got to in your PhD so far. To everyone watching, if you'd like to ask Tristan a question, there is a question and answer section to the side. I've got a really big list of questions, so I'm just going to churn through mine unless anyone else pipes in. So firstly, so this is a desk-based study. So if you could have another 3 years and go out and do some field work, what would you do?
Another 3 years would be nice, yeah. So I kind of am doing that a little bit in the next stage. So the next stage, I'm zooming into a particular place to use as a case study to look at the actual potential that exists below the resolution of this resource. So that's in Inverness, so that's why I showed that picture at the start. So like I was saying, this is a national scale desktop resource. So it's intended for planners or councillors to be able to assess whether it's worth getting someone in to actually look at the sediments a bit more closely, and particularly with paleo valleys and berry valleys, of which there's one in Inverness. I'm interested in what the actual typical distribution of sediments between those highly productive sands and gravels are compared to the clays, and how you can overcome those kind of engineering problems when you actually get to the site specific level. Yeah, so looking a bit more at that kind of stuff is where I'm going to in the future, and if I had another 3 years to do it, that would be lovely.
Awesome. We've had another question online, and it's asking if all your data is publicly available that you're using for your PhD, and are all your outputs going to be publicly available as well?
Yeah, I haven't published them yet, but that is certainly the intention, yeah. Because I realise that I've benefited a lot in having accessible data sets and being able to use them, and fundamentally there's no point in doing research if nobody can look at it or read it or understand it. So yeah, I want it to be.
Brilliant. Another one of my questions is, so obviously this is a national study of Scotland. Has this been done anywhere else? And also, where would you go next in the world if you had to do this in a different country?
Yeah, so it's been done in different areas, but in slightly different ways, because again, it's down to those sort of those FAIR principles again, and depends on what data actually exists in different areas. So there are plenty of similar studies, but because the different national geological surveys have collected they've done different studies and they've got different data and different data sets. It means you can't do the exact same thing. So I suppose what's interesting about one thing that's interesting about my map is I called it geothermal favorability instead of pure potential, because it's not actually producing a figure of how much power you could extract from the subsurface, and that's because we don't have enough of that data across Scotland to be able to do that on a national scale, but you can do that in some other places. So there are similar things, but to varying degrees. Yeah.
Awesome.
Yeah, sorry. So where would I go after that? Or somewhere warm would be nice, I think. Yeah.
Yeah, we can both attest that a lot of Scottish energy is going on heating, especially at the moment. We've had another question online. This is from Kevin Mallon, and he asks, having drilled many ground source heat pump schemes in Scotland and water wells, do you think the whole supply chain is robust enough to make your research a reality?
Probably not currently. The idea is that it is partially partially promotion of ground source heat pumps to show town planners that it's something that's worthwhile to actually look into, and then they might find there's actually more resource there than they imagined. I don't envisage every single place that has some potential to actually go for it, because you've also got to think about sort of a holistic approach to energy transition and what other energy solutions there are for different places. And there might be a different technology which suits the demographics of an area or the economic activities in the area better than this does. And there's also the sort of question of a just transition in that sense of one of the findings from this was that, you know, some of the big cities, you could whack in a big district heat network and you could cut off a lot of carbon emissions that way. And that's a very sort of numerical approach to the issue. But when you start thinking about people and sort of societies, you've got to consider that those big cities will be able to decarbonize in different ways and have different options. Whereas a community-based approach for what could be a much smaller program such as this on a rural area might give that rural community a lot more than if they were going to go for a different technology. So it's about making sure that there's a just transition in that people don't get left behind. So it's not only big cities that get decarbonized, it's also appropriate for rural communities and such like that. So yeah, I don't see it happening everywhere, but I do see it happening more than it is currently.
Brilliant. We've had another question online. This one says, have you considered looking at open loop in hard rock aquifers, i.e. not superficials? Many ground source heat pumps in Norway and Sweden both intersect solid rock geology, which have much better thermal conductivities.
So it's kind of a yes and no. So the project which I came into was specifically looking at superficial aquifers and their resource. So that's why there's that focus on superficial deposits. Have I considered it outside of that remit and going, well, that's also a really useful resource and something to look into? Yeah, and I think it's a question of expense, and whatever is the more cost-effective option is what's going to take hold, kind of thing. And that's just a reality of how everything works. So yeah, so I see the bedrock resource being very important as well. I'm more focused on the superficials, but I think there's room for both.
Awesome. I will ask one final question unless anything else comes through online. So if I'm a local council in Scotland, and I'm looking to decarbonise one of my small towns with a heat network. What are the major selling points of an open loop kind of superficial aquifer geothermal system, as opposed to, I'm also considering sewage, sewage work heat pumps, or river source, or waste from heat?
I think it's that you should be able to, if you have what an up-to-date district heat network design, you should be able to integrate all those different types of heat sources into a common system where it can all be utilized in an efficient way. So by combining those alongside the low temperature geothermal in the superficials, you can create a more robust resource which is less susceptible to variations in the heat resource which comes from those other types. So again, I think it's about bringing lots of different heat sources, but also lots of different technologies together. So by integrating them, you form an infrastructure which is less likely to fail or less likely to come under strain.
Fantastic. Well, thank you so much for joining us today. If anyone has any further questions for Tristan, you can send an email to the Women in Geothermal UK team, and we can forward them on to him. A little note before we all go, our next Wednesday with Wing is in December for our Christmas special with Helen Doran from Project Inner Space. And there will also be a small Christmas quiz and an opportunity to win a hamper. So the registration links for that will be up soon, and we hope to see you all there. Thank you again to Tristan, and have a good evening all.
Thank you very much.